Okay, so during the break, I just draft some templates. Okay, it's ugly, but I still hope that you can watch it clearly. Okay, so this is the topology of the buck converter. So this is the transistor, this is the diode, input voltage, output voltage, and there are also two components. This is the inductor and this is the capacitor. Okay, and some of the parameters are given. Those are very important. And we are going to draw 6 waveforms. Okay, 6 waveforms. So the first one is the Q waveform. Q waveform is very simple, either 1 or 0. Right? But before that, before drawing the Q waveform, we need to determine 2 parameters. So the first one is the on interval, and then the other one is the switching interval. Okay, so for the switching interval, we can calculate the value from switching frequency. So this is the first parameters that we need to determine. 5 microseconds. Okay, so we can label 5 here. 5 microseconds. And then the other one is T on, right? T on is equal to DTS. So D here is given. So we don't need to do any calculation. 3 microseconds. So here we can label 3. And here is 8 and 10. Okay, and then we change the color. So during on state, Q is equal to 1. Off state, Q is equal to 0. So the waveform should look like this. Okay. Okay, and then this is done. Second waveform, VA. So VA is the voltage across the dial, right? So during the on state, actually we don't need to memorize the waveform. We can just need to look at the topology. Okay. So during the on state, this is completely on, and this is reverse bias. So reverse bias, it means that it can block the input voltage. So during the on state, VA should be equal to Vin. So Vin is equal to, it is given, right? It is given is 20 volt. Okay, so here we can just enter 20. And then during the off state, it is forward bias. So here VA is equal to 0. Repeat every cycle. This is the waveform. Okay, and then we also need to determine its average value. So this average value is capital B with the subscript A. Okay, and here this one should be equal to V naught. Okay, average. If you don't remember, no problem. As I mentioned, you can just calculate this area and then divide it by TS, and then you will know the average VA should be equal to V naught. Okay, and V naught here is not given. Okay, so we need to do the calculation. Okay, so this is the buck converter. So V naught is equal to dV in, and then substitute the parameters. So we will have 12 volt. So 12 volt. We contribute here. So 12 volt. Okay, so this is done for the second waveform. And then VL, inductor voltage. So inductor voltage, we should remember, right? So in the DC steady state, the average inductor voltage should be equal to 0. So it means that during the on state should be positive, and then during off state is to be negative. Otherwise, the average value should not be equal to 0. Correct? Okay, so we can do it one by one. So during on state, so VL is equal to what? So here is the VL, right? So according to the KVL, we have 3 sources here, okay? And the voltage polarities of the inductor and the load are the same, okay? So we can simply write down this. Okay, so okay, and so we can substitute the parameters and then know, okay, so this is 8 volt. So 8 volt, we can go here 8. And how about off during the off state? So during the off state, it is simpler. It is because VA is equal to 0, right? So we only have one parameter left. So 8 is equal to minus 12 volt. And here can contribute here. This is minus 12. Okay, so according to those information, we can draw our waveform. And for this one, this is also the pulse string waveform, but the average value should be equal to 0, so we don't need to label the dashed line again. Okay, so this is done. And then IL ripple. So for the IL ripple, so it should look like this, right? Look like this. Okay, up and down, up and down. And then actually we can do some calculation if it is not given in the problem. Okay, so we have this equation. We should have the L here. It is because it comes from the basic definition of the inductor voltage, right? This one. Okay, the delta IL is here. Okay, and 1 over L, and so this should be the VL. So VL during the on state, or we can use the off state this time. No problem. Okay, so it depends. So here I may show you this one. Okay, and then this one L is given 24. And then V naught, we just calculate 12. 1 minus, this is also given, and then TS 5 microsecond. Okay, so we have this. Okay, so this is the peak to peak. Okay, peak to peak inductor current. Okay, so we need to divide it into half. 5 ampere here, and here is minus 0.5, and then such that the peak to peak value is equal to 1 ampere. Okay, okay, and then the next thing we need to do is to determine if it goes up or go down during the on state. Okay, so we just need to look at the topology. Okay, so during the on state, it is completely on, and so the input current can keep flowing through or keep flowing into the inductor. So IL should increase against time during the on state. All right, so in that sense, we just need to draw the IL ripple goes up against time during the on state, and then down during the off state, something like that. Okay, so this is done. Okay, so IL, So IL is the shape or the trend here is identical to IL, but I hope that you still remember. Okay, so IL actually just do the offset, okay, or shift upwards, okay, by I naught. That I naught is capital I naught. Sorry, capital IL. Okay, capital IL. But here, capital IL is equal to I naught. Do you still remember? It is because the average capacitor currents should be equal to zero. Should be equal to zero in the DC steady state. So that's why the average IL should be equal to I naught. Okay, so average IL is equal to I naught, and I naught here, actually, we need to check. Okay, so P naught is given here. Okay, so P naught is given here, and we have the V naught, so we can use this very simple relationship and substitute the given parameters, and this one we just calculate here. Okay, so we have this. Okay, so we put it here. It is the average current. Okay, and this is the dashed line, and then we can draw IL now. So to draw this, we need to keep the delta P to peak value, the P to peak value, right? So this one should be 1.167 minus 0.5, and this one should be 1.167 plus 0.5. So it is equal to 1.667, and this is equal to minus 667. Okay, and then we just need to draw like this. All right. Okay, so this is done for IL. Last one. Sorry for overrun a bit. Okay, this is the last one. Okay, so during on state, look at the topology. During the on state, I in should be equal to IL. Okay, so here is very simple. We just need to copy this part to here. Okay, so here the peak is 1.667. This is ampere. Okay, and this one is 0.667. Right, and then what happens during the what happened for the I in during the off state? So during off state, this is off, right? So I in should be equal to 0. Okay, so here should be equal to 0. So this is the waveform. Okay, but still one more thing to do. This is the average input current. Okay, so average input current actually we can derive the equation according to this one. Okay, so we can write down like this. It is because P is equal to VI, and then again substitute the parameters. This will be equal to 0.7 ampere. Okay, so 0.7 ampere should be somewhere here. 0.7, and then there's the slide. Capital I in. Okay, so that is the solution. Any question?